In this video, we will talk about such important components of machine learning as feature engineering, feature selection, and feature scaling. What is feature engineering? Feature engineering means to select proper features so that our machine learning algorithm will work properly. Features are some parameters which characterize our information from which we have to learn in a very efficient way. So some parameters, some values which characterize our input information in the best way. For example, let's consider a rough example. We have information about time. Yes, we have two images. In one figure, it's time 7 minutes to 4, and in another it's something like 8 or 10 o'clock. So we can represent this time by the position of the clock arrows in the XY plane, yes, which is shown in the middle. But another even more efficient way to represent the information is to write the angles of each clock arrow. And this seems to be the most efficient and simple, very, very concise way to represent information about the current time in this situation. So this is just a rough example. Or, for example, I propose you to consider the following artificial, but I hope quite representative example. We have data about house prices depending on the length and width of the house. General parameters, the length and width of the house, and then its price in the thousands of dollars. So we have such information. You can see, for example, the first house has width and length and width as 38 and 34 meters, and it costs $650,000. So and so on. Okay, we can apply the well-known to us from previous videos methods of linear regression to predict the price based on length and width of the house. And we can get the optimal parameters in the mean square sense, and somehow we can see on this graph that both price depends on the length of the house, but not in a straight line, and also a dependence of price depending on the width is very close to it, not a straight line, some vague information depending on the width of the house. So we can get the optimal linear approximation of price of the house for the price of the house depending on its dimensions. But we see that mean standard deviation error is $66,000. So we can see that this prediction is not accurate, to say at least. The error of approximation is too high. However, if we add additional parameter, which is area of the house in square meters, it's a product of length and width, we can get by applying the linear regression for the three parameters, we get the following dependence, which is shown at the top of this slide. So price depends on the length with coefficient minus 0.02, also on the width with a coefficient minus 0.01, and it depends on the area with the coefficient of 0.5, and also a free term which is equal to $1,000. It's just a coincidence in this situation that these coefficients are look so simple. And we have a mean standard deviation error as $2,33,000, which is much less than the previous situation, when we did not take the area into account, area of the house. So, and then if we take just one parameter, we abandon length and width, and we use just area of the house. We also get a perfect approximation in this case with the same mean standard deviation error, $2.33,000. And the prediction of the price shown at the bottom is just 0.5 multiply the area of the house plus $640. So this is much simpler. And in this case, we see that we had two parameters, but from them we can engineer we can create just one parameter, the area of the house, which in fact represents the input information in the best way. And this is the art of feature engineering. I hope this example helps us to understand it. Also, I want to show just one example where there are two classes of data. This is more appropriate for the classification task, not for the linear regression, but nevertheless, I want to show you how the transformation of input parameters can help us to better distinguish the input information to our machine learning problem. If we have, for example, on the left upper corner, we have two classes of data, yes, represented by blue and red dots. And just if we transform these features into the polar coordinates from Cartesian to polar coordinates, we see how much well they are separated. Yes, and also, or we can go from the 2 dimensions to 3 dimensions by introducing new variables. From x, y, we go to x squared, y squared, and product x and y. And we also see that these data are now separated just by some plane. But this is more specific for the classification problem, and we will talk about it in one of our next videos. So, if we have some set of features, here we have p features, x1, x2, xp, we can transfer them to second order features. Not just the initial features, but also the cross products of them and also their squares. This is a technique which helps very often in some practical problems. So we can consider example, but before that we must take notice that if we use too many features is also not very good, because we have a risk of overfitting. We talked about overfitting problem in our previous video. Also, much more memory often is required to store the information about the problem. And also we have less computational stability of algorithm, especially in the case of finite precision for the storage of our data. So in some cases, we would need the dimensionality reduction to reduce the number of our features. I want to show it you on one specific example. In this case, we have nine variables, but when transformed to the second order features, there are already 54 of them. We have 54 features, and then we apply linear regression methods, linear regression. For these 54 features, we try to make linear prediction of one target variable. I will not mention it exactly the details for the simplicity of explanation, but below we see the 54 coefficients W of linear regression, which were calculated by the linear regression algorithm, by the gradient descent effect. And we see that all these coefficients have the different absolute values. For example, the 14th coefficient has the largest value. So it may talk to us that this feature is of most importance. This is the most important feature. The more is weighting coefficient for the particular feature, the more important is this feature. So, for example, here I write down the features starting from the most important ones. So in the descending order of the absolute values of the weighting coefficients. So, and in this case, we see that x5 squared is the most important feature. For example, x5 without the second degree is on the fourth position. x7 has position 11. So we see that we can in this way we see that we can engineer new features. Maybe some of them do not have the exact physical or well understandable sense, but nevertheless we engineer some new features which can be effectively used to solve such problems. Okay, this is what I wanted to say about feature engineering and the connected with it task of feature selection. Also, we must note that such analysis, which I just have shown, when we select some features based on their weighting coefficients, this can be done only in the case when our features have the same range. So they are very closer. For example, around 1 or around 2, not higher than 1 or not higher than 2. So the variables must be properly scaled. So they will have the similar ranges or similar. They will have similar magnitudes. How it is done? The usual technique for this is to subtract the mean value of the variable or the feature and then divide it by standard deviation of square root from variance. It's a standard deviation of some variable. Also, the fragment of Python code is also shown here. I will show you an example. For example, let's recall the cars mode dataset, which we used, which we showed several meetings before. And here we can see that the weight of the car has one range, about several thousands of kilograms. The horsepower has values about 100. Parameter characterizing acceleration has values from 10 to 20. And the target variable, which we want to predict, the miles per gallon consumption, so parameter characterizing consumption, is from 10 to 40, about something like this. And we see that these variables, these features, have different ranges. And the target variable, miles per gallon, also has another range. So they all must be scaled. So we will operate with the variables with similar ranges. This is what we obtain after doing such scaling. You can see now that almost all of the variables are now in the range from -1 to 1, although some of them are, we have some outliers, so-called outliers. How to deal with outliers we'll also consider in the future. But now the range of all the variables is basically the same. And we can analyze such problem now of predicting consumption based on other parameters much more efficiently. I want to show you the graph of the cost function or the loss function. Yes, when there is no scaling, we do not have a distinct convex form of loss function, the least square, which is calculated by the least squares rule. So the gradient descent method, for example, may not converge. In fact, it very often doesn't converge in such situations. But just because our features have the different, because the features have different magnitudes, they are of different ranges. Yes, but here, when we apply scaling, when we scale both mile per gallon consumption and the weight of the car, the parameters, these features are now basically of the same range, and now we have a distinct convex feature of the cost function, and so its minimum can be efficiently and easily found, for example, by gradient descent method. So the scaling of the features is very important. And in this case, when we are interested in prediction of the miles per gallon based on the weight of the car, we can predict its value in such a simple way from the scaled weight of the car, minus 0.86 multiplied scaled weight of the car. And of course, we can come back when reverse this transformation. And at the bottom of this slide, we can, by the reverse transformation, we can obtain now non-scaled prediction of miles per gallon based on the weight of the car. So feature scaling is very important, and it will also be used in many more situations, which we will consider in the future. So this is what I wanted to say about important aspects of machine learning as feature engineering, feature selection, and feature scaling. Thank you very much for your kind attention.